Chapter 1. Introduction to the Atmosphere. Earth's atmosphere is unique. No other planet in our solar system has an atmosphere with the exact mixture of gases or the heat and moisture conditions necessary to sustain life as we know it. The gases that make up Earth's atmosphere and the controls to which they are subject are vital to our existence. In this chapter we begin our examination of the ocean of air in which we all must live. After completing this chapter, you should be able to distinguish between weather and climate and name the basic elements of weather and climate. List several important atmospheric hazards and identify those that are storm-related. Construct a hypothesis and distinguish between a scientific hypothesis and a scientific theory. List and describe Earth's four major spheres. Define system and explain why Earth can be thought of as a system. List the major gases composing Earth's atmosphere and identify those components that are most important meteorologically. Explain why ozone depletion is a significant global issue. Interpret a graph that shows changes in air pressure from Earth's surface to the top of the atmosphere. Sketch and label a graph showing the thermal structure of the atmosphere. Distinguish between homosphere and heterosphere. Focus on the atmosphere. Introduction to the atmosphere. Weather and climate. Weather influences our everyday activities, our jobs, and our health and comfort. Many of us pay little attention to the weather unless we are inconvenienced by it or when it adds to our enjoyment of outdoor activities. Nevertheless, there are few other aspects of our physical environment that affect our lives more than the phenomena we collectively call the weather. Weather in the United States. The United States occupies an area that stretches from the tropics to the Arctic Circle. It has thousands of miles of coastline and extensive regions that are far from the influence of the ocean. Some landscapes are mountainous, and others are dominated by plains. It is a place where Pacific storms strike the west coast, while the east is sometimes influenced by events in the Atlantic and the Gulf of Mexico. For those in the center of the country, it is common to experience weather events triggered when frigid southward-bound Canadian air masses clash with northward-moving tropical ones from the Gulf of Mexico. Stories about weather are a routine part of the daily news. Articles and items about the effects of heat, cold, floods, drought, fog, snow, ice, and strong winds are commonplace. Figure 1.1. Memorable weather events occur everywhere on our planet. The United States likely has the greatest variety of weather of any country in the world. Severe weather events, such as tornadoes, flash floods, and intense thunderstorms, as well as hurricanes and blizzards, are collectively more frequent and more damaging in the United States than in any other nation. Beyond its direct impact on the lives of individuals, the weather has a strong effect on the world economy, by influencing agriculture, energy use, water resources, transportation, and industry. Weather clearly influences our lives a great deal. Yet it is also important to realize that people influence the atmosphere and its behavior as well. Figure 1.2. There are, and will continue to be, significant political and scientific decisions to make involving these impacts. Answers to questions regarding air pollution and its control and the effects of various emissions on global climate are important examples. So there is a need for increased awareness and understanding of our atmosphere and its behavior. Meteorology, weather, and climate. The subtitle of this book includes the word meteorology. Meteorology is the scientific study of the atmosphere and the phenomena that we usually refer to as weather. Along with geology, oceanography, and astronomy, meteorology is considered one of the earth sciences, the sciences that seek to understand our planet. It is important to point out that there are not strict boundaries among the earth sciences. In many situations, these sciences overlap. Moreover, all of the earth sciences involve an understanding and application of knowledge and principles from physics, chemistry, and biology. You will see many examples of this fact in your study of meteorology. Acted on by the combined effects of Earth's motions and energy from the Sun, our planet's formless and invisible envelope of air reacts by producing an infinite variety of weather, which in turn creates the basic pattern of global climates. Although not identical, weather and climate have much in common. Weather is constantly changing, sometimes from hour to hour and at other times from day to day. It is a term that refers to the state of the atmosphere at a given time and place. Whereas changes in the weather are continuous and sometimes seemingly erratic, it is nevertheless possible to arrive at a generalization of these variations. Such a description of aggregate weather conditions is termed climate. It is based on observations that have been accumulated over many decades. Climate is often defined simply as average weather, but this is an inadequate definition. In order to accurately portray the character of an area, variations and extremes must also be included, as well as the probabilities that such departures will take place. For example, it is necessary for farmers to know the average rainfall during the growing season, and it is also important to know the frequency of extremely wet and extremely dry years. Thus, climate is the sum of all statistical weather information that helps describe a place or region. Maps similar to the one in Figure 1.3 are familiar to everyone who checks the weather report in the morning newspaper or on a television station. In addition to showing predicted high temperatures for the day, this map shows other basic weather information about cloud cover, precipitation, and fronts. Suppose you were planning a vacation trip to an unfamiliar place. You would probably want to know what kind of weather to expect. Such information would help as you selected clothes to pack and could influence decisions regarding activities you might engage in during your stay. Unfortunately, weather forecasts that go beyond a few days are not very dependable. Thus, it would not be possible to get a reliable weather report about the conditions you are likely to encounter during your vacation. Instead, you might ask someone who is familiar with the area about what kind of weather to expect. Are thunderstorms common? Does it get cold at night? Are the afternoons sunny? What you are seeking is information about the climate, the conditions that are typical for that place. Another useful source of such information is the great variety of climate tables, maps, and graphs that are available. For example, the map in Figure 1.4 shows the average percentage of possible sunshine in the United States for the month of November, and the graph in Figure 1.5 shows average daily high and low temperatures for each month, as well as extremes, for New York City. Such information could, no doubt, help as you planned your trip. But it is important to realize that climate data cannot predict the weather. Although the place may usually, climatically, be warm, sunny, and dry during the time of your planned vacation, you may actually experience cool, overcast, and rainy weather. There is a well-known saying that summarizes this idea: climate is what you expect, but weather is what you get. The nature of both weather and climate is expressed in terms of the same basic elements, those quantities or properties that are measured regularly. The most important are 1. The temperature of the air, 2. The humidity of the air, 3. The type and amount of cloudiness, 4. The type and amount of precipitation, 5. The pressure exerted by the air, and 6. The speed and direction of the wind. These elements constitute the variables by which weather patterns and climate types are depicted. Although you will study these elements separately at first, keep in mind that they are very much interrelated. A change in one of the elements often produces changes in the others. Students sometimes ask, does meteorology have anything to do with meteors? Yes, there is a connection. Most people use the word meteor when referring to solid particles, meteoroids, that enter Earth's atmosphere from space and burn up due to friction, shooting stars. The term meteorology was coined in 340 BC, when the Greek philosopher Aristotle wrote a book titled Meteorologica, which included explanations of atmospheric and astronomical phenomena. In Aristotle's day, anything that fell from or was seen in the sky was called a meteor. Today we distinguish between particles of ice or water in the atmosphere, called hydrometeors, and extraterrestrial objects called meteoroids, or meteors. Atmospheric hazards, assault by the elements. Natural hazards are a part of living on Earth. Every day they adversely affect literally millions of people worldwide and are responsible for staggering damages. Some, such as earthquakes and volcanic eruptions, are geological. Many others are related to the atmosphere. Occurrences of severe weather are far more fascinating than ordinary weather phenomena. A spectacular lightning display generated by a severe thunderstorm can elicit both awe and fear, Figure 1.6a. Of course, hurricanes and tornadoes attract a great deal of much-deserved attention. A single tornado outbreak or hurricane can cause billions of dollars in property damage, much human suffering, and many deaths. Of course, other atmospheric hazards adversely affect us. Some are storm-related, such as blizzards, hail, and freezing rain. Others are not direct results of storms. Heat waves, cold waves, fog, wildfires, and drought are important examples, Figure 1.6b. In some years the loss of human life due to excessive heat or bitter cold exceeds that caused by all other weather events combined. Moreover, although severe storms and floods usually generate more attention, droughts can be just as devastating and carry an even bigger price tag. Between 1980 and 2010, the United States experienced 99 weather-related disasters in which overall damages and costs reached or exceeded $1 billion, Figure 1.7. The combined costs of these events exceeded $725 billion, normalized to $2007. During the decade 1999-2008, an average of 629 direct weather fatalities occurred per year in the United States. During this span, the annual economic impacts of adverse weather on the national highway system alone exceeded $40 billion, and weather-related air traffic delays caused $4.2 billion in annual losses. At appropriate places throughout this book, you will have an opportunity to learn about atmospheric hazards. 2 entire chapters, Chapter 10 and Chapter 11, focus almost entirely on hazardous weather. In addition, a number of the book's special interest boxes are devoted to a broad variety of severe and hazardous weather, including heat waves, winter storms, floods, dust storms, drought, mudflows, and lightning. Every day our planet experiences an incredible assault by the atmosphere, so it is important to develop an awareness and understanding of these significant weather events. The nature of scientific inquiry. As members of a modern society, we are constantly reminded of the benefits derived from science. But what exactly is the nature of scientific inquiry? Developing an understanding of how science is done and how scientists work is an important theme in this book. You will explore the difficulties of gathering data and some of the ingenious methods that have been developed to overcome these difficulties. You will also see examples of how hypotheses are formulated and tested, as well as learn about the development of some significant scientific theories. All science is based on the assumption that the natural world behaves in a consistent and predictable manner that is comprehensible through careful, systematic study. The overall goal of science is to discover the underlying patterns in nature and then to use this knowledge to make predictions about what should or should not be expected, given certain facts or circumstances. For example, by understanding the processes and conditions that produce certain cloud types, meteorologists are often able to predict the approximate time and place of their formation. The development of new scientific knowledge involves some basic logical processes that are universally accepted. To determine what is occurring in the natural world, scientists collect scientific facts through observation and measurement. The types of facts that are collected often seek to answer a well-defined question about the natural world, such as why does fog frequently develop in this place, or what causes rain to form in this cloud type. Because some error is inevitable, the accuracy of a particular measurement or observation is always open to question. Nevertheless, these data are essential to science and serve as a springboard for the development of scientific theories. Box 1-1. Hypothesis. Once facts have been gathered and principles have been formulated to describe a natural phenomenon, investigators try to explain how or why things happen in the manner observed. They often do this by constructing a tentative, or untested, explanation, which is called a scientific hypothesis. It is best if an investigator can formulate more than one hypothesis to explain a given set of observations. If an individual scientist is unable to devise multiple hypotheses, others in the scientific community will almost always develop alternative explanations. A spirited debate frequently ensues. As a result, extensive research is conducted by proponents of opposing hypotheses, and the results are made available to the wider scientific community in scientific journals. Before a hypothesis can become an accepted part of scientific knowledge, it must pass objective testing and analysis. If a hypothesis cannot be tested, it is not scientifically useful, no matter how interesting it might seem. The verification process requires that predictions be made based on the hypothesis being considered and the predictions be tested by being compared against objective observations of nature. Put another way, hypotheses must fit observations other than those used to formulate them in the first place. Hypotheses that fail rigorous testing are ultimately discarded. The history of science is littered with discarded hypotheses. One of the best known is the Earth-centered model of the universe, a proposal that was supported by the apparent daily motion of the Sun, Moon, and stars around Earth. Theory. When a hypothesis has survived extensive scrutiny and when competing ones have been eliminated, a hypothesis may be elevated to the status of a scientific theory. In everyday language we may say, "That's only a theory." But a scientific theory is a well-tested and widely accepted view that the scientific community agrees best explains certain observable facts. Some theories that are extensively documented and extremely well supported are comprehensive in scope. An example from the earth sciences is the theory of plate tectonics, which provides the framework for understanding the origin of mountains, earthquakes, and volcanic activity. It also explains the evolution of continents and ocean basins through time. As you will see in Chapter 14, this theory also helps us understand some important aspects of climate change through long spans of geologic time. Box 1-1. Monitoring Earth from space. Scientific facts are gathered in many ways, including through laboratory experiments and field observations and measurements. Satellites provide another very important source of data. Satellite images give us perspectives that are difficult to gain from more traditional sources, Figure 1a. Moreover, the high-tech instruments aboard many satellites enable scientists to gather information from remote regions where data are otherwise scarce. The image in Figure 1b is from NASA's Tropical Rainfall Measuring Mission, TRMM. TRMM is a research satellite designed to expand our understanding of Earth's water, hydrologic, cycle and its role in our climate system. By covering the region between the latitudes 35 degrees north and 35 degrees south, it provides much-needed data on rainfall and the heat release associated with rainfall. Many types of measurements and images are possible. Instruments aboard the TRMM satellite have greatly expanded our ability to collect precipitation data. In addition to recording data for land areas, this satellite provides extremely precise measurements of rainfall over the oceans where conventional land-based instruments cannot see. This is especially important because much of Earth's rain falls in ocean-covered tropical areas, and a great deal of the globe's weather-producing energy comes from heat exchanges involved in the rainfall process. Until the TRMM, information on the intensity and amount of rainfall over the tropics was scanty. Such data are crucial to understanding and predicting global climate change. Scientific methods. The processes just described, in which scientists gather facts through observations and formulate scientific hypotheses and theories, is called the scientific method. Contrary to popular belief, the scientific method is not a standard recipe that scientists apply in a routine manner to unravel the secrets of our natural world. Rather, it is an endeavor that involves creativity and insight. Rutherford and Algren put it this way: inventing hypotheses or theories to imagine how the world works and then figuring out how they can be put to the test of reality is as creative as writing poetry, composing music, or designing skyscrapers. There is not a fixed path that scientists always follow that leads unerringly to scientific knowledge. Nevertheless, many scientific investigations involve the following steps. 1. A question is raised about the natural world. 2. Scientific data are collected that relate to the question, Figure 1.8. 3. Questions are posed that relate to the data, and one or more working hypotheses are developed that may answer these questions. 4. Observations and experiments are developed to test the hypotheses. 5. The hypotheses are accepted, modified, or rejected, based on extensive testing. 6. Data and results are shared with the scientific community for critical and further testing. Other scientific discoveries may result from purely theoretical ideas that stand up to extensive examination. Some researchers use high-speed computers to simulate what is happening in the real world. These models are useful when dealing with natural processes that occur on very long time scales or take place in extreme or inaccessible locations. Still, other scientific advancements have been made when a totally unexpected happening occurred during an experiment. These serendipitous discoveries are more than pure luck, as Louis Pasteur stated, in the field of observation, chance favors only the prepared mind. Scientific knowledge is acquired through several avenues, so it might be best to describe the nature of scientific inquiry as the methods of science rather than the scientific method. In addition, it should always be remembered that even the most compelling scientific theories are still simplified explanations of the natural world. Students sometimes ask, in class you compared a hypothesis to a theory. How is each one different from a scientific law? A scientific law is a basic principle that describes a particular behavior of nature that is generally narrow in scope and can be stated briefly, often as a simple mathematical equation. Because scientific laws have been shown time and time again to be consistent with observations and measurements, they are rarely discarded. Laws may, however, require modifications to fit new findings. For example, Newton's laws of motion are still useful for everyday applications. NASA uses them to calculate satellite trajectories, but they do not work at velocities approaching the speed of light. For these circumstances, they have been supplanted by Einstein's theory of relativity. Students sometimes ask, who provides all the data needed to prepare a weather forecast? Data from every part of the globe are needed to produce accurate weather forecasts. The World Meteorological Organization, WMO, was established by the United Nations to coordinate scientific activity related to weather and climate. It consists of 187 member states and territories, representing all parts of the globe. Its World Weather Watch provides up-to-the-minute standardized observations through member-operated observation systems. This global system involves more than 15 satellites, 10,000 land observation and 7,300 ship stations, hundreds of automated data buoys, and thousands of aircraft. Earth's spheres. The images in Figure 1.9 are considered to be classics because they let humanity see Earth differently than ever before. Figure 1.9a, known as Earthrise, was taken when the Apollo 8 astronauts orbited the Moon for the first time in December 1968. As the spacecraft rounded the Moon, Earth appeared to rise above the lunar surface. Figure 1.9b, referred to as the blue marble, is perhaps the most widely reproduced image of Earth. It was taken in December 1972 by the crew of Apollo 17 during the last manned lunar mission. These early views profoundly altered our conceptualizations of Earth and remain powerful images decades after they were first viewed. Seen from space, Earth is breathtaking in its beauty and startling in its solitude. The photos remind us that our home is, after all, a planet small, self-contained, and in some ways even fragile. Bill Anders, the Apollo 8 astronaut who took the Earthrise photo, expressed it this way: "We came all this way to explore the Moon, and the most important thing is that we discovered the Earth." As we look closely at our planet from space, it becomes apparent that Earth is much more than rock and soil. In fact, the most conspicuous features in Figure 1.9a are not continents but swirling clouds suspended above the surface of the vast global ocean. These features emphasize the importance of water on our planet. The closer view of Earth from space shown in Figure 1.9b helps us appreciate why the physical environment is traditionally divided into three major parts: the solid Earth, the water portion of our planet, and Earth's gaseous envelope. It should be emphasized that our environment is highly integrated and is not dominated by rock, water, or air alone. It is instead characterized by continuous interactions as air comes in contact with rock, rock with water, and water with air. Moreover, the biosphere, the totality of life forms on our planet, extends into each of the three physical realms and is an equally integral part of the planet. The interactions among Earth's four spheres are incalculable. Figure 110 provides us with one easy-to-visualize example. The shoreline is an obvious meeting place for rock, water, and air. In this scene, ocean waves that were created by the drag of air moving across the water are breaking against the rocky shore. The force of the water can be powerful, and the erosional work that is accomplished can be great. On a human scale, Earth is huge. Its surface area occupies 500 million square kilometers, 193 million square miles. We divide this vast planet into four independent parts. Because each part loosely occupies a shell around Earth, we call them spheres. The four spheres include the geosphere, solid Earth, the atmosphere, gaseous envelope, the hydrosphere, water portion, and the biosphere, life. It is important to remember that these spheres are not separated by well-defined boundaries, rather, each sphere is intertwined with all of the others. In addition, each of Earth's four major spheres can be thought of as being composed of numerous interrelated parts. The geosphere. Beneath the atmosphere and the ocean is the solid Earth, or geosphere. The geosphere extends from the surface to the center of the planet, a depth of about 6,400 kilometers, nearly 4,000 miles, making it by far the largest of Earth's four spheres. Based on compositional differences, the geosphere is divided into three principal regions: the dense inner sphere, called the core, the less dense mantle, and the crust, which is the light and very thin outer skin of Earth. Soil, the thin veneer of material at Earth's surface that supports the growth of plants, may be thought of as part of all four spheres. The solid portion is a mixture of weathered rock debris, geosphere, and organic matter from decayed plant and animal life, biosphere. The decomposed and disintegrated rock debris is the product of weathering processes that require air, atmosphere, and water, hydrosphere. Air and water also occupy the open spaces between the solid particles. The atmosphere. Earth is surrounded by a life-giving gaseous envelope called the atmosphere, figure 111. When we watch a high-flying jet plane cross the sky, it seems that the atmosphere extends upward for a great distance. However, when compared to the thickness, radius, of the solid Earth, about 6,400 kilometers 4,000 miles, the atmosphere is a very shallow layer. More than 99% of the atmosphere is within 30 kilometers, 20 miles, of Earth's surface. This thin blanket of air is nevertheless an integral part of the planet. It not only provides the air that we breathe but also acts to protect us from the dangerous radiation emitted by the sun. The energy exchanges that continually occur between the atmosphere and Earth's surface and between the atmosphere and space produce the effects we call weather. If, like the Moon, Earth had no atmosphere, our planet would not only be lifeless, but many of the processes and interactions that make the surface such a dynamic place could not operate. The hydrosphere. Earth is sometimes called the blue planet. More than anything else, water makes Earth unique. The hydrosphere is a dynamic mass that is continually on the move, evaporating from the oceans to the atmosphere, precipitating to the land, and running back to the ocean again. The global ocean is certainly the most prominent feature of the hydrosphere, blanketing nearly 71% of Earth's surface to an average depth of about 3,800 meters, 12,500 feet. It accounts for about 97% of Earth's water, figure 112. However, the hydrosphere also includes the fresh water found in clouds, streams, lakes, and glaciers, as well as that found underground. Although these latter sources constitute just a tiny fraction of the total, they are much more important than their meager percentage indicates. Clouds, of course, play a vital role in many weather and climate processes. In addition to providing the fresh water that is so vital to life on land, streams, glaciers, and groundwater are responsible for sculpting and creating many of our planet's varied landforms. The biosphere. The biosphere includes all life on Earth, figure 113. Ocean life is concentrated in the sunlit surface waters of the sea. Most life on land is also concentrated near the surface, with tree roots and burrowing animals reaching a few meters underground and flying insects and birds reaching a kilometer or so above the surface. A surprising variety of life forms are also adapted to extreme environments. For example, on the ocean floor, where pressures are extreme and no light penetrates, there are places where vents spew hot, mineral-rich fluids that support communities of exotic life forms. On land, some bacteria thrive in rocks as deep as 4 kilometers, 2.5 miles, and in boiling hot springs. Moreover, air currents can carry microorganisms many kilometers into the atmosphere. But even when we consider these extremes, life still must be thought of as being confined to a narrow band very near Earth's surface. Plants and animals depend on the physical environment for the basics of life. However, organisms do more than just respond to their physical environment. Through countless interactions, life forms help maintain and alter their physical environment. Without life, the makeup and nature of the geosphere, hydrosphere, and atmosphere would be very different. Earth as a system. Anyone who studies Earth soon learns that our planet is a dynamic body with many separate but highly interactive parts, or spheres. The atmosphere, hydrosphere, biosphere, and geosphere and all of their components can be studied separately. However, the parts are not isolated. Each is related in many ways to the others, producing a complex and continuously interacting whole that we call the Earth system. Earth system science. A simple example of the interactions among different parts of the Earth system occurs every winter as moisture evaporates from the Pacific Ocean and subsequently falls as rain in the hills of Southern California, triggering destructive debris flows, figure 114. The processes that move water from the hydrosphere to the atmosphere and then to the geosphere have a profound impact on the physical environment and on the plants and animals, including humans, that inhabit the affected regions. Scientists have recognized that in order to more fully understand our planet, they must learn how its individual components, land, water, air, and life forms, are interconnected. This endeavor, called Earth System Science, aims to study Earth as a system composed of numerous interacting parts, or subsystems. Using an interdisciplinary approach, those who practice Earth system science attempt to achieve the level of understanding necessary to comprehend and solve many of our global environmental problems. A system is a group of interacting, or interdependent, parts that form a complex whole. Most of us hear and use the term system frequently. We may service our car's cooling system, make use of the city's transportation system, and be a participant in the political system. A news report might inform us of an approaching weather system. Further, we know that Earth is just a small part of a larger system known as the Solar System, which in turn is a subsystem of an even larger system called the Milky Way galaxy. The Earth System. The Earth system has a nearly endless array of subsystems in which matter is recycled over and over again. One example that is described in Box 1-2 traces the movements of carbon among Earth's 4 spheres. It shows us, for example, that the carbon dioxide in the air and the carbon in living things and in certain rocks is all part of a subsystem described by the carbon cycle. The parts of the Earth system are linked so that a change in one part can produce changes in any or all of the other parts. For example, when a volcano erupts, lava from Earth's interior may flow out at the surface and block a nearby valley. This new obstruction influences the region's drainage system by creating a lake or causing streams to change course. The large quantities of volcanic ash and gases that can be emitted during an eruption might be blown high into the atmosphere and influence the amount of solar energy that can reach Earth's surface. The result could be a drop in air temperatures over the entire hemisphere. Where the surface is covered by lava flows or a thick layer of volcanic ash, existing soils are buried. This causes the soil-forming processes to begin anew to transform the new surface material into soil, Figure 115. The soil that eventually forms will reflect the interactions among many parts of the Earth system, the volcanic parent material, the climate, and the impact of biological activity. Of course, there would also be significant changes in the biosphere. Some organisms and their habitats would be eliminated by the lava and ash, whereas new settings for life, such as the lake, would be created. The potential climate change could also impact sensitive life forms. The Earth system is characterized by processes that vary on spatial scales from fractions of millimeters to thousands of kilometers. Time scales for Earth's processes range from milliseconds to billions of years. As we learn about Earth, it becomes increasingly clear that despite significant separations in distance or time, many processes are connected, and a change in one component can influence the entire system. The Earth system is powered by energy from 2 sources. The Sun drives external processes that occur in the atmosphere, hydrosphere, and at Earth's surface. Weather and climate, ocean circulation, and erosional processes are driven by energy from the Sun. Earth's interior is the second source of energy. Heat remaining from when our planet formed and heat that is continuously generated by radioactive decay power the internal processes that produce volcanoes, earthquakes, and mountains. Humans are part of the Earth system, a system in which the living and non-living components are entwined and interconnected. Therefore, our actions produce changes in all the other parts. When we burn gasoline and coal, dispose of our wastes, and clear the land, we cause other parts of the system to respond, often in unforeseen ways. Throughout this book you will learn about some of Earth's subsystems, including the hydrologic system and the climate system. Remember that these components and we humans are all part of the complex interacting whole we call the Earth system. Composition of the atmosphere. In the days of Aristotle, air was thought to be one of four fundamental substances that could not be further divided into constituent components. The other three substances were fire, earth, soil, and water. Even today the term air is sometimes used as if it were a specific gas, which of course it is not. The envelope of air that surrounds our planet is a mixture of many discrete gases, each with its own physical properties, in which varying quantities of tiny solid and liquid particles are suspended. Major components. The composition of air is not constant, it varies from time to time and from place to place, see box 1.3. If the water vapor, dust, and other variable components were removed from the atmosphere, we would find that its makeup is very stable up to an altitude of about 80 kilometers, 50 miles. As you can see in figure 116, two gases, nitrogen and oxygen, make up 99% of the volume of clean, dry air. Although these gases are the most plentiful components of the atmosphere and are of great significance to life on Earth, they are of little or no importance in affecting weather phenomena. The remaining 1% of dry air is mostly the inert gas argon, 0.93%, plus tiny quantities of a number of other gases. Carbon dioxide. Carbon dioxide, although present in only minute amounts, 0.0391%, or 391 parts per million, is nevertheless a meteorologically important constituent of air. Carbon dioxide is of great interest to meteorologists because it is an efficient absorber of energy emitted by Earth and thus influences the heating of the atmosphere. Although the proportion of carbon dioxide in the atmosphere is relatively uniform, its percentage has been rising steadily for more than a century. Figure 117 is a graph showing the growth in atmospheric CO2 since 1958. Much of this rise is attributed to the burning of ever-increasing quantities of fossil fuels, such as coal and oil. Some of this additional carbon dioxide is absorbed by the waters of the ocean or is used by plants, but more than 40% remains in the air. Estimates project that by sometime in the second half of the 21st century, carbon dioxide levels will be twice as high as pre-industrial levels. Most atmospheric scientists agree that increased carbon dioxide concentrations have contributed to a warming of Earth's atmosphere over the past several decades and will continue to do so in the decades to come. The magnitude of such temperature changes is uncertain and depends partly on the quantities of CO2 contributed by human activities in the years ahead. The role of carbon dioxide in the atmosphere and its possible effects on climate are examined in more detail in chapters 2 and 14. Box 1-2. The carbon cycle, one of Earth's subsystems. To illustrate the movement of material and energy in the Earth system, let us take a brief look at the carbon cycle, figure 1c. Pure carbon is relatively rare in nature. It is found predominantly in two minerals, diamond and graphite. Most carbon is bonded chemically to other elements to form compounds such as carbon dioxide, calcium carbonate, and the hydrocarbons found in coal and petroleum. Carbon is also the basic building block of life as it readily combines with hydrogen and oxygen to form the fundamental organic compounds that compose living things. In the atmosphere, carbon is found mainly as carbon dioxide, CO2. Atmospheric carbon dioxide is significant because it is a greenhouse gas, which means it is an efficient absorber of energy emitted by Earth and thus influences the heating of the atmosphere. Because many of the processes that operate on Earth involve carbon dioxide, this gas is constantly moving into and out of the atmosphere. For example, through the process of photosynthesis, plants absorb carbon dioxide from the atmosphere to produce the essential organic compounds needed for growth. Animals that consume these plants, or consume other animals that eat plants, use these organic compounds as a source of energy and, through the process of respiration, return carbon dioxide to the atmosphere. Plants also return some CO2 to the atmosphere via respiration. Further, when plants die and decay or are burned, this biomass is oxidized, and carbon dioxide is returned to the atmosphere. Not all dead plant material decays immediately back to carbon dioxide. A small percentage is deposited as sediment. Over long spans of geologic time, considerable biomass is buried with sediment. Under the right conditions, some of these carbon-rich deposits are converted to fossil fuels, coal, petroleum, or natural gas. Eventually some of the fuels are recovered, mined or pumped from a well, and burned to run factories and fuel our transportation system. One result of fossil fuel combustion is the release of huge quantities of CO2 into the atmosphere. Certainly one of the most active parts of the carbon cycle is the movement of CO2 from the atmosphere to the biosphere and back again. Carbon also moves from the geosphere and hydrosphere to the atmosphere and back again. For example, volcanic activity early in Earth's history is thought to be the source of much of the carbon dioxide found in the atmosphere. One way that carbon dioxide makes its way back to the hydrosphere and then to the solid Earth is by first combining with water to form carbonic acid, H2CO3, which then attacks the rocks that compose the geosphere. One product of this chemical weathering of solid rock is the soluble bicarbonate ion, 2HCO3, which is carried by groundwater and streams to the ocean. Here water-dwelling organisms extract this dissolved material to produce hard parts, shells, of calcium carbonate, CaCO3. When the organisms die, these skeletal remains settle to the ocean floor as biochemical sediment and become sedimentary rock. In fact, the geosphere is by far Earth's largest depository of carbon, where it is a constituent of a variety of rocks, the most abundant being limestone, figure 1d. Eventually the limestone may be exposed at Earth's surface, where chemical weathering will cause the carbon stored in the rock to be released to the atmosphere as CO2. In summary, carbon moves among all four of Earth's major spheres. It is essential to every living thing in the biosphere. In the atmosphere, carbon dioxide is an important greenhouse gas. In the hydrosphere, carbon dioxide is dissolved in lakes, rivers, and the ocean. In the geosphere, carbon is contained in carbonate-rich sediments and sedimentary rocks and is stored as organic matter dispersed through sedimentary rocks and as deposits of coal and petroleum. Variable components. Air includes many gases and particles that vary significantly from time to time and place to place. Important examples include water vapor, aerosols, and ozone. Although usually present in small percentages, they can have significant effects on weather and climate. Water vapor. The amount of water vapor in the air varies considerably, from practically none at all up to about 4% by volume. Why is such a small fraction of the atmosphere so significant? The fact that water vapor is the source of all clouds and precipitation would be enough to explain its importance. However, water vapor has other roles. Like carbon dioxide, it has the ability to absorb heat given off by Earth, as well as some solar energy. It is therefore important when we examine the heating of the atmosphere. When water changes from one state to another, such as from a gas to a liquid or a liquid to a solid, see Figure 4.3, it absorbs or releases heat. This energy is termed latent heat, which means hidden heat. As you will see in later chapters, water vapor in the atmosphere transports this latent heat from one region to another, and it is the energy source that drives many storms. Box 1.3. Origin and evolution of Earth's atmosphere. The air we breathe is a stable mixture of 78% nitrogen, 21% oxygen, nearly 1% argon, and small amounts of gases such as carbon dioxide and water vapor. However, our planet's original atmosphere 4.6 billion years ago was substantially different. Earth's primitive atmosphere. Early in Earth's formation, its atmosphere likely consisted of gases most common in the early solar system: hydrogen, helium, methane, ammonia, carbon dioxide, and water vapor. The lightest of these gases, hydrogen and helium, escaped into space because Earth's gravity was too weak to hold them. Most of the remaining gases were probably scattered into space by strong solar winds, vast streams of particles, from a young active sun. All stars, including the Sun, apparently experience a highly active stage early in their evolution, during which solar winds are very intense. Earth's first enduring atmosphere was generated by a process called outgassing, through which gases trapped in the planet's interior are released. Outgassing from hundreds of active volcanoes still remains an important planetary function worldwide, Figure 1e. However, early in Earth's history, when massive heating and fluid-like motion occurred in the planet's interior, the gas output must have been immense. Based on our understanding of modern volcanic eruptions, Earth's primitive atmosphere probably consisted of mostly water vapor, carbon dioxide, and sulfur dioxide, with minor amounts of other gases and minimal nitrogen. Most importantly, free oxygen was not present. Oxygen in the atmosphere. As Earth cooled, water vapor condensed to form clouds, and torrential rains began to fill low-lying areas, which became the oceans. In those oceans, nearly 3.5 billion years ago, photosynthesizing bacteria began to release oxygen into the water. During photosynthesis, organisms use the sun's energy to produce organic material, energetic molecules of sugar containing hydrogen and carbon, from carbon dioxide, CO2, and water, H2O. The first bacteria probably used hydrogen sulfide, H2S, as the source of hydrogen rather than water. One of the earliest bacteria, cyanobacteria, once called blue-green algae, began to produce oxygen as a byproduct of photosynthesis. Initially, the newly released oxygen was readily consumed by chemical reactions with other atoms and molecules, particularly iron, in the ocean, Figure 1f. Once the available iron satisfied its need for oxygen and as the number of oxygen-generating organisms increased, oxygen began to build in the atmosphere. Chemical analyses of rocks suggest that a significant amount of oxygen appeared in the atmosphere as early as 2.2 billion years ago and increased steadily until it reached stable levels about 1.5 billion years ago. Obviously, the availability of free oxygen had a major impact on the development of life and vice versa. Earth's atmosphere evolved together with its life forms from an oxygen-free envelope to an oxygen-rich environment. Another significant benefit of the oxygen explosion is that oxygen molecules, O2, readily absorb ultraviolet radiation and rearrange themselves to form ozone, O3. Today, ozone is concentrated above the surface in a layer called the stratosphere, where it absorbs much of the ultraviolet radiation that strikes the upper atmosphere. For the first time, Earth's surface was protected from this type of solar radiation, which is particularly harmful to DNA. Marine organisms had always been shielded from ultraviolet radiation by the oceans, but the development of the atmosphere's protective ozone layer made the continents more hospitable. Students sometimes ask, could you explain a little more about why the graph in Figure 117 has so many ups and downs? Sure. Carbon dioxide is removed from the air by photosynthesis, the process by which green plants convert sunlight into chemical energy. In spring and summer, vigorous plant growth in the extensive land areas of the northern hemisphere removes carbon dioxide from the atmosphere, so the graph takes a dip. As winter approaches, many plants die or shed leaves. The decay of organic matter returns carbon dioxide to the air, causing the graph to spike upward. Aerosols. The movements of the atmosphere are sufficient to keep a large quantity of solid and liquid particles suspended within it. Although visible dust sometimes clouds the sky, these relatively large particles are too heavy to stay in the air very long. Still, many particles are microscopic and remain suspended for considerable periods of time. They may originate from many sources, both natural and human-made, and include sea salts from breaking waves, fine soil blown into the air, smoke and soot from fires, pollen and microorganisms lifted by the wind, ash and dust from volcanic eruptions, and more. Figure 118a. Collectively, these tiny solid and liquid particles are called aerosols. Aerosols are most numerous in the lower atmosphere near their primary source, Earth's surface. Nevertheless, the upper atmosphere is not free of them, because some dust is carried to great heights by rising currents of air, and other particles are contributed by meteoroids that disintegrate as they pass through the atmosphere. From a meteorological standpoint, these tiny, often invisible particles can be significant. First, many act as surfaces on which water vapor may condense, an important function in the formation of clouds and fog. Second, aerosols can absorb or reflect incoming solar radiation. Thus, when an air pollution episode is occurring or when ash fills the sky following a volcanic eruption, the amount of sunlight reaching Earth's surface can be measurably reduced. Finally, aerosols contribute to an optical phenomenon we have all observed, the varied hues of red and orange at sunrise and sunset. Figure 118b. Ozone. Another important component of the atmosphere is ozone. It is a form of oxygen that combines 3 oxygen atoms into each molecule, O3. Ozone is not the same as the oxygen we breathe, which has 2 atoms per molecule, O2. There is very little ozone in the atmosphere. Overall, it represents just 3 out of every 10 million molecules. Moreover, its distribution is not uniform. In the lowest portion of the atmosphere, ozone represents less than 1 part in 100 million. It is concentrated well above the surface in a layer called the stratosphere, between 10 and 50 kilometers, 6 and 31 miles. In this altitude range, oxygen molecules, O2, are split into single atoms of oxygen, O, when they absorb ultraviolet radiation emitted by the sun. Ozone is then created when a single atom of oxygen, O, and a molecule of oxygen, O2, collide. This must happen in the presence of a third, neutral molecule that acts as a catalyst by allowing the reaction to take place without itself being consumed in the process. Ozone is concentrated in the 10 to 50 km height range because a crucial balance exists there. The ultraviolet radiation from the sun is sufficient to produce single atoms of oxygen, and there are enough gas molecules to bring about the required collisions. The presence of the ozone layer in our atmosphere is crucial to those of us who are land dwellers. The reason is that ozone absorbs the potentially harmful ultraviolet, UV, radiation from the sun. If ozone did not filter a great deal of the ultraviolet radiation, and if the sun's UV rays reached the surface of Earth undiminished, land areas on our planet would be uninhabitable for most life as we know it. Thus, anything that reduces the amount of ozone in the atmosphere could affect the well-being of life on Earth. Just such a problem is described in the next section. Ozone depletion, a global issue. The loss of ozone high in the atmosphere as a consequence of human activities is a serious global-scale environmental problem. For nearly a billion years, Earth's ozone layer has protected life on the planet. However, over the past half-century, people have unintentionally placed the ozone layer in jeopardy by polluting the atmosphere. The most significant of the offending chemicals are known as chlorofluorocarbons, CFCs. They are versatile compounds that are chemically stable, odorless, non-toxic, non-corrosive, and inexpensive to produce. Over several decades, many uses were developed for CFCs, including as coolants for air conditioning and refrigeration equipment, as cleaning solvents for electronic components, as propellants for aerosol sprays, and in the production of certain plastic foams. Students sometimes ask, isn't ozone some sort of pollutant? Yes, you're right. Although the naturally occurring ozone in the stratosphere is critical to life on Earth, it is regarded as a pollutant when produced at ground level because it can damage vegetation and be harmful to human health. Ozone is a major component in a noxious mixture of gases and particles called photochemical smog. It forms as a result of reactions triggered by sunlight that occur among pollutants emitted by motor vehicles and industries. Chapter 13 provides more information about this. No one worried about how CFCs might affect the atmosphere until three scientists, Paul Crutzen, F. Sherwood Rowland, and Mario Molina, studied the relationship. In 1974 they alerted the world when they reported that CFCs were probably reducing the average concentration of ozone in the stratosphere. In 1995 these scientists were awarded the Nobel Prize in Chemistry for their pioneering work. They discovered that because CFCs are practically inert, that is, not chemically active, in the lower atmosphere, a portion of these gases gradually makes its way to the ozone layer, where sunlight separates the chemicals into their constituent atoms. The chlorine atoms released this way, through a complicated series of reactions, have the net effect of removing some of the ozone. The Antarctic ozone hole. Although ozone depletion by CFCs occurs worldwide, measurements have shown that ozone concentrations take an especially sharp drop over Antarctica during the southern hemisphere spring, September and October. Later, during November and December, the ozone concentration recovers to more normal levels, Figure 119. Between 1980, when it was discovered, and the early 2000s, this well-publicized ozone hole intensified and grew larger until it covered an area roughly the size of North America, Figure 120. The hole is caused in part by the relatively abundant ice particles in the south polar stratosphere. The ice boosts the effectiveness of CFCs in destroying ozone, thus causing a greater decline than would otherwise occur. The zone of maximum depletion is confined to the Antarctic region by a swirling upper-level wind pattern. When this vortex weakens during the late spring, the ozone-depleted air is no longer restricted and mixes freely with air from other latitudes where ozone levels are higher. A few years after the Antarctic ozone hole was discovered, scientists detected a similar but smaller ozone thinning in the vicinity of the North Pole during spring and early summer. When this pool breaks up, parcels of ozone-depleted air move southward over North America, Europe, and Asia. Effects of ozone depletion. Because ozone filters out most of the damaging UV radiation in sunlight, a decrease in its concentration permits more of these harmful wavelengths to reach Earth's surface. What are the effects of the increased ultraviolet radiation? Each 1% decrease in the concentration of stratospheric ozone increases the amount of UV radiation that reaches Earth's surface by about 2%. Therefore, because ultraviolet radiation is known to induce skin cancer, ozone depletion seriously affects human health, especially among fair-skinned people and those who spend considerable time in the sun. The fact that up to 500,000 cases of these cancers occur in the United States annually means that ozone depletion could ultimately lead to many thousands more cases each year. In addition to raising the risk of skin cancer, an increase in damaging UV radiation can negatively impact the human immune system, as well as promote cataracts, a clouding of the eye lens that reduces vision and may cause blindness if not treated. The effects of additional UV radiation on animal and plant life are also important. There is serious concern that crop yields and quality will be adversely affected. Some scientists also fear that increased UV radiation in the Antarctic will penetrate the waters surrounding the continent and impair or destroy the microscopic plants, called phytoplankton, that represent the base of the food chain. A decrease in phytoplankton, in turn, could reduce the population of copepods and krill that sustain fish, whales, penguins, and other marine life in the high latitudes of the southern hemisphere. Montreal Protocol. What has been done to protect the atmosphere's ozone layer? Realizing that the risks of not curbing CFC emissions were difficult to ignore, an international agreement known as the Montreal Protocol on Substances that Deplete the Ozone Layer was concluded under the auspices of the United Nations in late 1987. The protocol established legally binding controls on the production and consumption of gases known to cause ozone depletion. As the scientific understanding of ozone depletion improved after 1987 and substitutes and alternatives became available for the offending chemicals, the Montreal Protocol was strengthened several times. More than 190 nations eventually ratified the treaty. The Montreal Protocol represents a positive international response to a global environment problem. As a result of the action, the total abundance of ozone-depleting gases in the atmosphere has started to decrease in recent years. According to the U.S. Environmental Protection Agency, US EPA, the ozone layer has not grown thinner since 1998 over most of the world. If the nations of the world continue to follow the provisions of the protocol, the decreases are expected to continue throughout the 21st century. Some offending chemicals are still increasing but will begin to decrease in coming decades. Between 2060 and 2075, the abundance of ozone-depleting gases is projected to fall to values that existed before the Antarctic ozone hole began to form in the 1980s. Vertical structure of the atmosphere. Extent of the atmosphere. Thermal structure of the atmosphere. To say that the atmosphere begins at Earth's surface and extends upward is obvious. However, where does the atmosphere end and where does outer space begin? There is no sharp boundary. The atmosphere rapidly thins as you travel away from Earth, until there are too few gas molecules to detect. Pressure changes. To understand the vertical extent of the atmosphere, let us examine the changes in atmospheric pressure with height. Atmospheric pressure is simply the weight of the air above. At sea level, the average pressure is slightly more than 1000 millibars. This corresponds to a weight of slightly more than 1 kilogram per square centimeter, 14.7 pounds per square inch. Obviously, the pressure at higher altitudes is less, figure 121. 1/2 of the atmosphere lies below an altitude of 5.6 kilometers, 3.5 miles. At about 16 kilometers, 10 miles, 90% of the atmosphere has been traversed, and above 100 kilometers, 62 miles, only 0.00003% of all the gases composing the atmosphere remain. At an altitude of 100 kilometers, the atmosphere is so thin that the density of air is less than could be found in the most perfect artificial vacuum at the surface. Nevertheless, the atmosphere continues to even greater heights. The truly rarefied nature of the outer atmosphere is described very well by Richard Craig. The Earth's outermost atmosphere, the part above a few hundred kilometers, is a region of extremely low density. Near sea level, the number of atoms and molecules in a cubic centimeter of air is about 2 times 10 raised to 19. Near 600 kilometers, it is only about 2 times 10 raised to 7, which is the sea level value divided by a million. At sea level, an atom or molecule can be expected, on the average, to move about 7 times 10 raised to -6 centimeters before colliding with another particle. At the 600 km level, this distance, called the mean free path, is about 10 kilometers. Near sea level, an atom or molecule, on the average, undergoes about 7 times 10 raised to 9 such collisions each second. Near 600 kilometers, this number is reduced to about 1 each minute. The graphic portrayal of pressure data, figure 121, shows that the rate of pressure decrease is not constant. Rather, pressure decreases at a decreasing rate with an increase in altitude until, beyond an altitude of about 35 kilometers, 22 miles, the decrease is negligible. Put another way, data illustrate that air is highly compressible, that is, it expands with decreasing pressure and becomes compressed with increasing pressure. Consequently, traces of our atmosphere extend for thousands of kilometers beyond Earth's surface. Thus, to say where the atmosphere ends and outer space begins is arbitrary and, to a large extent, depends on what phenomenon one is studying. It is apparent that there is no sharp boundary. In summary, data on vertical pressure changes show that the vast bulk of the gases making up the atmosphere is very near Earth's surface and that the gases gradually merge with the emptiness of space. When compared with the size of the solid Earth, the envelope of air surrounding our planet is indeed very shallow. Temperature changes. By the early 20th century much had been learned about the lower atmosphere. The upper atmosphere was partly known from indirect methods. Data from balloons and kites had revealed that the air temperature dropped with increasing height above Earth's surface. This phenomenon is felt by anyone who has climbed a high mountain and is obvious in pictures of snow-capped mountaintops rising above snow-free lowlands, figure 122. Although measurements had not been taken above a height of about 10 kilometers, 6 miles, scientists believed that the temperature continued to decline with height to a value of absolute zero, -273 degrees Celsius, at the outer edge of the atmosphere. In 1902, however, the French scientist Léon-Philippe Tisserand-de-Bort refuted the notion that temperature decreases continuously with an increase in altitude. In studying the results of more than 200 balloon launchings, Tisserand-de-Bort found that the temperature stopped decreasing and leveled off at an altitude between 8 and 12 kilometers, 5 and 7.5 miles. This surprising discovery was at first doubted, but subsequent data gathering confirmed his findings. Later, through the use of balloons and rocket sounding techniques, the temperature structure of the atmosphere up to great heights became clear. Today the atmosphere is divided vertically into 4 layers on the basis of temperature, figure 123. Troposphere. The bottom layer in which we live, where temperature decreases with an increase in altitude, is the troposphere. The term was coined in 1908 by Tisserand-de-Bort and literally means the region where air turns over, a reference to the appreciable vertical mixing of air in this lowermost zone. The temperature decrease in the troposphere is called the environmental lapse rate. Its average value is 6.5 degrees Celsius per kilometer, 3.5 degrees Fahrenheit per 1,000 feet, a figure known as the normal lapse rate. It should be emphasized, however, that the environmental lapse rate is not a constant but rather can be highly variable and must be regularly measured. To determine the actual environmental lapse rate as well as gather information about vertical changes in air pressure, wind, and humidity, radiosondes are used. A radiosonde is an instrument package that is attached to a balloon and transmits data by radio as it ascends through the atmosphere, figure 124. The environmental lapse rate can vary during the course of a day with fluctuations of the weather, as well as seasonally and from place to place. Sometimes shallow layers where temperatures actually increase with height are observed in the troposphere. When such a reversal occurs, a temperature inversion is said to exist. The temperature decrease continues to an average height of about 12 kilometers, 7.5 miles. Yet the thickness of the troposphere is not the same everywhere. It reaches heights in excess of 16 kilometers, 10 miles, in the tropics, but in polar regions it is more subdued, extending to 9 kilometers, 5.5 miles, or less, figure 125. Warm surface temperatures and highly developed thermal mixing are responsible for the greater vertical extent of the troposphere near the equator. As a result, the environmental lapse rate extends to great heights, and despite relatively high surface temperatures below, the lowest tropospheric temperatures are found aloft in the tropics and not at the poles. The troposphere is the chief focus of meteorologists because it is in this layer that essentially all important weather phenomena occur. Almost all clouds and certainly all precipitation, as well as all our violent storms, are born in this lowermost layer of the atmosphere. This is why the troposphere is often called the weather sphere. Stratosphere. Beyond the troposphere lies the stratosphere. The boundary between the troposphere and the stratosphere is known as the tropopause. Below the tropopause, atmospheric properties are readily transferred by large-scale turbulence and mixing, but above it, in the stratosphere, they are not. In the stratosphere, the temperature at first remains nearly constant to a height of about 20 kilometers, 12 miles, before it begins a sharp increase that continues until the stratopause is encountered at a height of about 50 kilometers, 30 miles, above Earth's surface. Higher temperatures occur in the stratosphere because it is in this layer that the atmosphere's ozone is concentrated. Recall that ozone absorbs ultraviolet radiation from the sun. Consequently, the stratosphere is heated by the sun. Although the maximum ozone concentration exists between 15 and 30 kilometers, 9 and 19 miles, the smaller amounts of ozone above this height range absorb enough UV energy to cause the higher observed temperatures. Mesosphere. In the third layer, the mesosphere, temperatures again decrease with height until at the mesopause, some 80 kilometers, 50 miles, above the surface, the average temperature approaches -90 degrees Celsius, -130 degrees Fahrenheit. The coldest temperatures anywhere in the atmosphere occur at the mesopause. The pressure at the base of the mesosphere is only about 1/1000th that at sea level. At the mesopause, the atmospheric pressure drops to just 1/1,000,000th that at sea level. Because accessibility is difficult, the mesosphere is one of the least explored regions of the atmosphere. The reason is that it cannot be reached by the highest flying airplanes and research balloons, nor is it accessible to the lowest orbiting satellites. Recent technical developments are just beginning to fill this knowledge gap. Thermosphere. The fourth layer extends outward from the mesopause and has no well-defined upper limit. It is the thermosphere, a layer that contains only a tiny fraction of the atmosphere's mass. In the extremely rarefied air of this outermost layer, temperatures again increase, due to the absorption of very short-wave, high-energy solar radiation by atoms of oxygen and nitrogen. Temperatures rise to extremely high values of more than 1000 degrees Celsius, 1800 degrees Fahrenheit, in the thermosphere. But such temperatures are not comparable to those experienced near Earth's surface. Temperature is defined in terms of the average speed at which molecules move. Because the gases of the thermosphere are moving at very high speeds, the temperature is very high. But the gases are so sparse that collectively they possess only an insignificant quantity of heat. For this reason, the temperature of a satellite orbiting Earth in the thermosphere is determined chiefly by the amount of solar radiation it absorbs and not by the high temperature of the almost non-existent surrounding air. If an astronaut inside were to expose his or her hand, the air in this layer would not feel hot. Vertical variations in composition. In addition to the layers defined by vertical variations in temperature, other layers, or zones, are also recognized in the atmosphere. Based on composition, the atmosphere is often divided into two layers, the homosphere and the heterosphere. From Earth's surface to an altitude of about 80 kilometers, 50 miles, the makeup of the air is uniform in terms of the proportions of its component gases. That is, the composition is the same as that shown earlier, in Figure 116. This lower uniform layer is termed the homosphere, the zone of homogeneous composition. In contrast, the very thin atmosphere above 80 kilometers is not uniform. Because it has a heterogeneous composition, the term heterosphere is used. Here the gases are arranged into four roughly spherical shells, each with a distinctive composition. The lowermost layer is dominated by molecular nitrogen, N2, next, a layer of atomic oxygen, O, is encountered, followed by a layer dominated by helium, He, atoms, and finally a region consisting largely of hydrogen, H, atoms. The stratified nature of the gases making up the heterosphere varies according to their weights. Molecular nitrogen is the heaviest, and so it is lowest. The lightest gas, hydrogen, is outermost. Ionosphere. Located in the altitude range between 80 to 400 kilometers, 50 to 250 miles, and thus coinciding with the lower portions of the thermosphere and heterosphere, is an electrically charged layer known as the ionosphere. Here molecules of nitrogen and atoms of oxygen are readily ionized as they absorb high-energy shortwave solar energy. In this process, each affected molecule or atom loses one or more electrons and becomes a positively charged ion, and the electrons are set free to travel as electric currents. Although ionization occurs at heights as great as 1,000 kilometers, 620 miles, and extends as low as perhaps 50 kilometers, 30 miles, positively charged ions and negative electrons are most dense in the range of 80 to 400 kilometers, 50 to 250 miles. The concentration of ions is not great below this zone because much of the short wavelength radiation needed for ionization has already been depleted. In addition, the atmospheric density at this level results in a large percentage of free electrons being swiftly captured by positively charged ions. Beyond the 400 km, 250 mile, upward limit of the ionosphere, the concentration of ions is low because of the extremely low density of the air. Because so few molecules and atoms are present, relatively few ions and free electrons can be produced. The electrical structure of the ionosphere is not uniform. It consists of 3 layers of varying ion density. From bottom to top, these layers are called the D, E, and F layers, respectively. Because the production of ions requires direct solar radiation, the concentration of charged particles changes from day to night, particularly in the D and E zones. That is, these layers weaken and disappear at night and reappear during the day. The uppermost layer, or F layer, on the other hand, is present both day and night. The density of the atmosphere in this layer is very low, and positive ions and electrons do not meet and recombine as rapidly as they do at lesser heights, where density is higher. Consequently, the concentration of ions and electrons in the F layer does not change rapidly, and the layer, although weak, remains through the night. The auroras. As best we can tell, the ionosphere has little impact on our daily weather. But this layer of the atmosphere is the site of one of nature's most interesting spectacles, the auroras, figure 126. The aurora borealis, northern lights, and its southern hemisphere counterpart, the aurora australis, southern lights, appear in a wide variety of forms. Sometimes the displays consist of vertical streamers in which there can be considerable movement. At other times the auroras appear as a series of luminous expanding arcs or as a quiet glow that has an almost fog-like quality. The occurrence of auroral displays is closely correlated in time with solar flare activity and, in geographic location, with Earth's magnetic poles. Solar flares are massive magnetic storms on the Sun that emit enormous amounts of energy and great quantities of fast-moving atomic particles. As the clouds of protons and electrons from the solar storm approach Earth, they are captured by its magnetic field, which in turn guides them toward the magnetic poles. Then, as the ions impinge on the ionosphere, they energize the atoms of oxygen and molecules of nitrogen and cause them to emit light, the glow of the auroras. Because the occurrence of solar flares is closely correlated with sunspot activity, auroral displays increase conspicuously at times when sunspots are most numerous. Introduction to the atmosphere in review. Meteorology is the scientific study of the atmosphere. Weather refers to the state of the atmosphere at a given time and place. It is constantly changing, sometimes from hour to hour and other times from day to day. Climate is an aggregate of weather conditions, the sum of all statistical weather information that helps describe a place or region. The nature of both weather and climate is expressed in terms of the same basic elements, those quantities or properties measured regularly. The most important elements are 1. Air temperature, 2. Humidity, 3. Type and amount of cloudiness, 4. Type and amount of precipitation, 5. Air pressure, and 6. The speed and direction of the wind. All science is based on the assumption that the natural world behaves in a consistent and predictable manner. The process by which scientists gather facts through observation and careful measurement and formulate scientific hypotheses and theories is often referred to as the scientific method. Earth's four spheres include the atmosphere, gaseous envelope, the geosphere, solid Earth, the hydrosphere, water portion, and the biosphere, life. Each sphere is composed of many interrelated parts and is intertwined with all the other spheres. Although each of Earth's four spheres can be studied separately, they are all related in a complex and continuously interacting whole that we call the Earth system. Earth system science uses an interdisciplinary approach to integrate the knowledge of several academic fields in the study of our planet and its global environmental problems. A system is a group of interacting parts that form a complex whole. The two sources of energy that power the Earth system are, 1. The Sun, which drives the external processes that occur in the atmosphere, hydrosphere, and at Earth's surface, and 2. Heat from Earth's interior that powers the internal processes that produce volcanoes, earthquakes, and mountains. Air is a mixture of many discrete gases, and its composition varies from time to time and place to place. After water vapor, dust, and other variable components are removed, two gases, nitrogen and oxygen, make up 99% of the volume of the remaining clean, dry air. Carbon dioxide, although present in only minute amounts, 0.0391%, or 391 ppm, is an efficient absorber of energy emitted by Earth and thus influences the heating of the atmosphere. The variable components of air include water vapor, dust particles, and ozone. Like carbon dioxide, water vapor can absorb heat given off by Earth as well as some solar energy. When water vapor changes from one state to another, it absorbs or releases heat. In the atmosphere, water vapor transports this latent, hidden, heat from one place to another, and it is the energy source that helps drive many storms. Aerosols, tiny solid and liquid particles, are meteorologically important because these often invisible particles act as surfaces on which water can condense and are also absorbers and reflectors of incoming solar radiation. Ozone, a form of oxygen that combines 3 oxygen atoms into each molecule, O3, is a gas concentrated in the 10 to 50 km height range in the atmosphere that absorbs the potentially harmful ultraviolet, UV, radiation from the sun. Over the past half-century, people have placed Earth's ozone layer in jeopardy by polluting the atmosphere with chlorofluorocarbons, CFCs, which remove some of the gas. Ozone concentrations take an especially sharp drop over Antarctica during the southern hemisphere spring, September and October. Ozone depletion seriously affects human health, especially among fair-skinned people and those who spend considerable time in the sun. The Montreal Protocol, concluded under the auspices of the United Nations, represents a positive international response to the ozone problem. No sharp boundary to the upper atmosphere exists. The atmosphere simply thins as you travel away from Earth, until there are too few gas molecules to detect. Traces of atmosphere extend for thousands of kilometers beyond Earth's surface. Using temperature as the basis, the atmosphere is divided into 4 layers. The temperature decrease in the troposphere, the bottom layer in which we live, is called the environmental lapse rate. Its average value is 6.5 degrees Celsius per kilometer, a figure known as the normal lapse rate. The environmental lapse rate is not a constant and must be regularly measured using radiosondes. The thickness of the troposphere is generally greater in the tropics than in polar regions. Essentially all important weather phenomena occur in the troposphere. Beyond the troposphere lies the stratosphere. The boundary between the troposphere and stratosphere is known as the tropopause. In the stratosphere, the temperature at first remains constant to a height of about 20 kilometers, 12 miles, before it begins a sharp increase due to the absorption of ultraviolet radiation from the sun by ozone. The temperatures continue to increase until the stratopause is encountered at a height of about 50 kilometers, 30 miles. In the mesosphere, the third layer, temperatures again decrease with height until the mesopause, some 80 kilometers, 50 miles, above the surface. The fourth layer, the thermosphere, with no well-defined upper limit, consists of extremely rarefied air. Temperatures here increase with an increase in altitude. The atmosphere is often divided into 2 layers, based on composition. The homosphere, zone of homogeneous composition, from Earth's surface to an altitude of about 80 kilometers, 50 miles, consists of air that is uniform in terms of the proportions of its component gases. Above 80 kilometers, the heterosphere, zone of heterogeneous composition, consists of gases arranged into 4 roughly spherical shells, each with a distinctive composition. The stratified nature of the gases in the heterosphere varies according to their weights. Occurring in the altitude range between 80 and 400 kilometers, 50 and 250 miles, is an electrically charged layer known as the ionosphere. Here molecules of nitrogen and atoms of oxygen are readily ionized as they absorb high-energy, shortwave solar energy. 3 layers of varying ion density make up the ionosphere. Auroras, the aurora borealis, northern lights, and its southern hemisphere counterpart the aurora australis, southern lights, occur within the ionosphere. Auroras form as clouds of protons and electrons ejected from the Sun during solar flare activity enter the atmosphere near Earth's magnetic poles and energize the atoms of oxygen and molecules of nitrogen, causing them to emit light, the glow of the auroras.